Today I'm going to talk about magnetic forces, what they are and what their effects are. But before I do that, I'm going to do a quick review of electric forces so we can see the comparison and likewise also the differences. So electric forces are forces between particles that have the property we call charge. And there are two types of charge. There's positive charge and negative charge. Which we typically denote as Q. Now, positive and negative charge interact with each other, and they do this by the electric field. So, two positive charges, if I have two charges, positive charges separated by some distance, we call the distance d, there's a force between those charges, and that force is a repulsive force because the charges are like charges. So the charge on the right pushes on the charge on the left with a force, and likewise the charge on the left pushes on the charge on the right with a force that is equal in magnitude but opposite in direction. And the strength of this force is given by Coulomb's law. So Coulomb's law says that the force between these two charges, say Q1 and Q2, well, the magnitude of this force is equal to 1 over 4 pi epsilon naught Q1 Q2 over d squared, where epsilon naught is the permittivity of free space with a value of 8.85 times 10 to the negative 12. We can figure out the units by simply noting that the left-hand side of the equation has to be equal to newtons. And then I have some 1 over some, let's say some constant k. The 4 pi is dimensionless, it's just a number. And then I have, up here I have units of charge, and the scientific units of charge is Coulomb. So I have Coulomb squared on the bottom, and then divided by length square. And the scientific unit for length is meter, so divided by meter squared. Now if I rearrange this equation to solve for k, you can see that the units of k, or my constant, I should say, is simply Coulomb squared over Newton meter squared. Okay, so again, those are the units of the constant, and this epsilon naught is equal to 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. This we call the permittivity of free space. And it's one of these fundamental constants of nature that determines the strength of the electric force. Permittivity of free space. All right, now this law up here is called Coulomb's law. And Coulomb's law is only valid when charges are stationary. It turns out that Coulomb's law is not entirely correct when charges are in motion with either a non-zero velocity relative to each other or a non-zero acceleration. A more general law which describes the interaction between these two charges is described in terms of Gauss's law. So what we say is that for these two charges to talk to each other, the force between them is mediated by something called the electric field. So force equals Q times E. And if I want to find the force, say, on the left charge, I have to take the electric field due to the right charge and multiply it by the charge at that point. So what we say is that charge Q2 mediates an electric field in all the space surrounding it. And this electric field is sort of like a substance that alters space. It's a vector field, meaning it has a point, meaning it has a value and a direction at every point in space. And charge Q sitting in the electric field of another charge therefore experiences a force. So this is traditionally how the action at a distance problem is solved. That is, to answer the question, how do Q1 and Q2 talk to each other when there's nothing but vacuum between them? When we look at this definition here, we can think of electric field as force per unit charge. If we're simply inventing this thing called the electric field, but it turns out the electric field turns out to be more physical than, say, the force is, if we start talking about energy. So the electric field due to a point charge is 1 over 4 pi epsilon naught Q over r squared, r hat, where r hat is that unit vector that points outwards. All right, now what happens if the charges are moving? Well, Coulomb's law only applies to the case of stationary charges. Sometimes Coulomb's law is referred to as the inverse square law. Notice very interestingly that this square at the bottom is exactly 2. And as far as has been able to be determined by experiment, it's not it's not roughly 2, but it's 2.0000, and there are several zeros here. I think as far as we've been able to measure experimentally, there's something like 8 or 9. Don't quote me on this. I would have to check the experimental data. But it's turned, as far as we can tell, it seems to be exactly 2, less than 1 part in a trillion, roughly. Okay, so that's very interesting. It's not just approximately 2, it's exactly 2. And this is very important because it turns out you can rewrite Coulomb's law in a more general form called Gauss's law. And Gauss's law reduces to Coulomb's law in the stationary case, but it's also a more general statement about electric fields. And what Gauss's law says is, if I calculate the electric flux through any closed surface, so if I take the integral of the electric field over some closed surface, which I'll call Gaussian surface G, every time I get Q enclosed over epsilon naught, just the total amount of charge in divided by epsilon naught. And you will have used this to calculate the electric field of highly symmetric charge distributions. So Gauss's law is written in here integral form, turns out to be one of the 4 fundamental equations of electromagnetism. It's a more general statement about the electric force than Coulomb's law is, although in this course we really only touch on Gauss's law to start with. In practice, what we typically use it for in an introductory course is simply to note that if I have a highly symmetric charge distribution, I can make symmetry arguments, which allows me to say the coordinate functional dependence of my electric field and what its components, what symmetry the electric field must obey. I can take that outside of the integral, and I can basically find the electric field due to a charge configuration which would otherwise be very difficult to do using Coulomb's law. So that is Gauss's law here. All right, now something else very interesting happens when charges are moving that we'll now talk about, and that is there is an additional force that arises that is entirely independent of the electric force, and that's called the magnetic force. Okay, and the magnetic force deals with, again, this property of charge. Now, it turns out that this force is only present when charge is moving. So let me make 2 points. First of all, when we talk about charge, charge is this very interesting property that are carried by fundamental particles, such as electrons or protons. Neutrons, it turns out, are charge neutral, although if we subdivide them, they're made up of quarks, which do have fractional charge. But what's very interesting is that charge only comes in 2 varieties, positive and negative. We might as well call those up or down, or black and white. But there's 2 different kinds that have opposite effects, and the magnitudes of those charges are identical to each other. So the positive charge, the basic unit of positive charge, is exactly equal but opposite in effect to the basic unit of negative charge. And those charges come in little chunks. So most electric phenomena that we observe in everyday life comes from the fact that we have large numbers of positive and negative charge. Now, in a typical atom and a typical material, the positive and the negative balance each other out, so there's no net charge and we don't experience the electric force. When we do experience the electric force that we can measure in terms of a coulombic interaction, that's where there is an imbalance between protons and electrons, such as how we started the quarter looking at the triboelectric effect, where you're stripping electrons off of a particular macroscopic object or adding electrons to it. Now, electric forces then exert force on charge. And what happens when it exerts a force on a charge? Well, it causes those charges to move. And when those charges move, it turns out there's another force called the magnetic force that arises just due to the fact that the charges themselves are moving. Now, you should already see that there's already a connection between electric and magnetic forces. Both have to do with the interaction of a field with charge. And whereas electric forces don't require, or I should say are present even when charges are not moving, magnetic forces are not present when charges are not moving. And I should be clear here, by moving, I mean if I only have 2 charges, they're moving relative to each other. In a normal object, there's going to be plenty of charge. While in a large macroscopic object, there's going to be a lot of charge that's moving in different directions. All right, so let's look a little bit more closely then at magnetic fields due to moving charges. So there's 2 sources of two basic sources of magnetic field or magnetic force. So the 2 sources are, one, we have a permanent magnet, and number 2, we have an electromagnet. Think of an electromagnet as a magnet that you can turn on or off by turning current on or off, electromagnet. Permanent magnet is a magnet that, by its natural properties, has a magnetic field, such as using a compass in the Earth's magnetic field. the Earth acts as a permanent magnet, and you can't simply turn the Earth's magnetic field on or off. Whereas in the case of an electromagnet, you can do that. Now, all magnetic force and therefore fields are due to moving charge. So what is moving in each case? Well, very simply, on the most fundamental level, it's always the electrons which are moving. Either the physical electron itself is moving, which would be what's happening in the case of an electromagnet. So I have a bunch of electrons. And if we're looking at a conventional conducting wire, here's my wire, you will recall that there are all these scattering sites, which I indicated by the blue dots. And these electrons, if there is an electric field that is applied due to a voltage source like a battery, these electrons will begin to drift through the material with a drift velocity. Right? So that net migration of the electrons as they move, there's going to be a large macroscopic number of electrons that are moving. Now, overall, they're moving very slow. It might be a fraction of a millimeter per second. But if you have Avogadro's number of electrons moving, those, even though they're not moving very fast, you have a large number of them. That's how you create a measurable magnetic field in an electromagnet. So further, what you'll do in an electromagnet is you can either have a very, very high current, meaning the charges you have a lot of charges moving fairly quickly. The other thing you can do is, in practice, is you can coil your wire. So, because what happens if you make a current larger and larger is there's more and more thermal scattering that takes place off of the positive ion cores, and the temperature of the wire will begin to increase. That is why we put fuse breakers in circuits in order to keep the wire from overheating. So an electromagnet might look something like this, where if I try to draw it from an angle here, I have a loop of wire, and there's a current in that loop of wire. This would produce a certain magnetic field, and the way I can determine the strength of this field is by, let's say on the left side of the wire here, I take my thumb on my right hand and I point it in the direction of the current, and my fingers will curl towards the direction of the field. So inside the loop, what I get is a magnetic field B that points to the right. Okay, and magnetic field is all around that wire. So it's going to actually look something, when I'm off the symmetry axis, we're going to see the field sort of have this type of shape as it kind of bends as I'm off that central axis. All right, now, if I want to make that field stronger, what I can do is I can coil the wire. Let's just say I add n turns to it. Right? If I add n turns, that should make the field n times as strong. So what you're going to get is you're going to get a field now where you have more and more lines. The density of the lines in this field diagram corresponds to the strength of the field. So let's talk about units for a second. What's the units for magnetic field? Units are the Tesla. And 1 Tesla equals 1 Newton second per Coulomb meter, which, if you break it down, is kilogram per Coulomb second. Now this might seem a little strange as far as units goes, but we'll talk about this in a moment and where this comes from. So electromagnets are produced primarily by moving electrons in wires. All right, now what about permanent magnets? Well, permanent magnets are produced primarily by spinning electrons. So I'm going to put spinning in quotation marks because spinning, to really understand electron spin, we need to know a little bit about quantum mechanics. But I'll give a classical analogy here, which will at least get us thinking about how there might be movement of charge. Electrons, which carry a negative unit of fundamental charge, which create this magnetic field we're calling B. Well, if I picture an electron as a ball, now this is not entirely correct. According to the elementary theory of particle physics, the electron is a point particle and can't be subdivided. That means it has no internal structure and has zero size. So to illustrate it as a ball doesn't really make a lot of sense, but let's just go with this analogy for a moment and see where it takes us. I'm going to paint the top half of the electron red, and I'm going to put a little N there. And underneath, I'm going to put a little S here, corresponding to North and South Pole. Now this electron, let's say it's spinning along an axis, which I'll call the rotation axis. All right, now, as this electron spins, if we picture the charge in that electron that's smeared out either uniformly over the surface or it's smeared out uniformly throughout the volume of the charge, while that charge density that's right on the rotation axis might not be moving, as you go out towards the edges, there is going to be a tangential velocity, and you're going to have charge basically moving around and around in a circle. That corresponds to moving charge. That is where you get permanent magnets from. Now, why don't we see magnetism in every material that we look at? Why, for example, is iron highly magnetic, but other materials such as copper don't seem to behave like magnets in ordinary experience and measurements? Well, the reason for this has to do with, really to understand this, we need a quantum theory of magnetism, but we'll just look at the basics here and try to understand from a chemistry perspective why this might be. In a typical atom, what you have is you have your nucleus, and which I'll illustrate by a little dot here, and then surrounding that nucleus, the nucleus contains protons with positive charge and neutrons that have no net charge. So there is the proton has, or sorry, the nucleus has a positive charge, and now I have electrons which orbit around the nucleus. And these electrons basically come in two varieties. There's two varieties of electrons that go around the nucleus. There's what we call a spin-up electron and a spin down. All right, now there's something called the Well, let me try to simplify this a little bit here. So electrons can only spin, if we were to think of a classical analogy here, they can only spin at a certain speed and in one of two directions. So this rotation axis can either point up, or I could rotate it around and it can point down. That would be spin up and spin down, and it can only spin at a certain rate. This is called the Bohr magnet. The value of this, the magnitude of this, is called the Bohr magneton. And in quantum mechanics, we call this the spin state of the electron. So while classically we could imagine spinning a ball at any speed with the rotation axis in any direction, quantum mechanically that doesn't happen. The electron is very interesting with its properties. It only spins in one particular direction at one particular rate, and we call that spin up or spin down. Now, there's a principle in quantum mechanics called the Pauli exclusion principle, which excludes identical fermions from occupying the same quantum state. So what we get is in each orbital surrounding the proton, and you might recall from chemistry that there's different kinds of orbitals that we call the s orbital, the p orbital, the d, and then we have hybrid orbitals, like sp, when you have bonding between different atoms to produce compounds, molecular compounds. But an orbital that is full is going to have a spin up and a spin down in that orbital, and we call that a diamagnetic atom if there's no unpaired electron spins. Diamagnetic atom, meaning that there's no net spin for that entire atom if there's no unpaired electrons. So a material with unpaired electron in a valence band, such as iron, can be, you can get a net spin accumulation with a macroscopic sample. So you get a large number of electrons in a number of iron atoms, say, or some other compound where there's only one electron in a particular orbital. Now there's an interaction between the spin up and spin up in neighboring atoms, and what you get, let's say, in a chunk of iron is, I'm going to illustrate the unpaired electron spins just by a single line. And what happens is one of those lines, that line is going to correspond to a whole bunch of electrons that have paired together due to the neighboring interactions in what we call domains. So there might be a bunch of domains that have spin pointing in this direction, then I can have another domain over here that points in this direction, and so forth. Now this still isn't strong enough to produce a large magnet, but if I take this chunk of iron and I put it in a magnetic field, what I end up with is all these domains with spins act like little compass needles in an external magnetic field, and they experience a torque and they twist to line up with the external field. So I get, once they spin, they'll all twist in the same direction. Once they're all lining up in the same direction, I get a net magnetic field to the right, in this case. All right, now this is what we call ferromagnetism. So permanent magnets are produced by the macroscopic alignment of unpaired electron spins, and ferromagnets tend to retain, like iron, tend to retain their magnetism. These spins all tend to stay locked together. They're only disrupted when there's some kind of thermal agitation, such as dropping a magnet several times will begin to cause these shock waves to cause these domains to unlock, or spins to basically break out of their locking patterns. And then you have other materials, such as paramagnetic material, which become magnetized in the presence of a strong magnet, like a ferromagnet. So for instance, the surface of your refrigerator it would be very expensive to produce a giant magnet over the surface of your refrigerator. So refrigerator surfaces are oftentimes paramagnetic in material, meaning that they become magnetized when a strong magnet is put in their presence, and that's why you can stick magnets to their surface. So the final kind of magnetism is called diamagnetism, and diamagnetism also produces a magnetic field, but it produces a magnetic field opposing the nearby field, and what that does is causes a repulsion. So you can cause little magnets to float on top of diamagnetic material. All right, most atoms are called diamagnetic if all their electrons are paired up in the orbitals. Remember, permanent magnets only come from unpaired electron spins. All right, well, there's much more that could be said about this, but suffice it to say, let's now talk a little bit about north and south poles. Although there are two sources of magnets, permanent and electromagnet, both have the same effect. And the effect is they produce a force on a moving charge. So let me draw a giant bar magnet here. This would be and that line right there is just something I'm painting on, and I'm going to paint this side red and put a north, and paint this side, leave it blank, and call that the south pole. Now, this magnet produces a magnetic field, and microscopically it's due to the fact that we have all of these unpaired electron spins inside the material which are lining up. So this net contribution produces a large, and I won't draw all of them there, but you get the picture here, that this field is produced by all these little spins lining up. Now you can kind of see what would happen if I was just to cut this magnet in half. I don't really separate the north and south pole. All that I get is I get two separate poles. Or I get two more magnets, I should say. So while you can separate positive and negative charges, you can never separate north and south pole. And in fact, physicists have been looking for a magnetic monopole, and it turns out if you could find one magnetic monopole in the entire universe, you could prove why electric charge is quantized. But that has never been seen, although for theoretical interests, physicists very much would like to find isolated magnetic monopoles. But as far as we can tell, even to an electron which has an inherent north and south pole, you can't slice an electron in half. You can't find a single north pole or a single south pole. We haven't seen anywhere in the universe. Okay, so here's my bar magnet. Now let me draw the magnetic field that corresponds to this bar magnet. So I have a field that goes like this. And inside the material, it actually, I could draw a few more lines to give you an idea of the shape of the field. But outside the magnet, the field always goes from north pole to south pole, whereas when you're inside the magnet, it goes from south to north. See these little magnetic dipoles, or these little electron spins, all want to line up. There's a magnetic torque on them to cause them to line up with the field. So this is the magnetic field B that is surrounding the bar magnet. And this is the exact same kind of field that's produced by electromagnets, but it's not the alignment of electron spins, it's a bunch of electrons which are drifting along in a wire. So similarly, this electromagnet right here, we could picture it as a bar magnet where your north pole is on this side, your south pole is on this side. And the field very much looks the same because outside here it kind of wraps around like this. So in summary then, two sources of magnetic fields, permanent an electromagnet, but it's all due to the motion of electrons, either by electrons drifting along, a large number of electrons drifting along, or a large number of electrons that are spinning in the same direction. So this is what produces magnetic fields, but how do we know that magnetic phenomenon is a real thing? And what do magnetic fields really do? Well, they produce a force, magnetic force. And this magnetic force, which I'll call F sub B, sometimes this is called the Lorentz Force law, is we have to ask the question, what do magnetic fields actually do? Well, they produce a force. Well, what do they produce a force on? Well, they produce a force on moving charge. So the Lorentz Force law can be written as QV crossed into B. And what this says is, when I take a charge that's moving with velocity v in a magnetic field B, it experiences a force. This cross product indicates that the force F is always perpendicular to the velocity vector and the magnetic field vector. And it's 0 when v and b are aligned. So the force always lies in a plane that's perpendicular. Well, the force always lies perpendicular to the VB plane. So think of the plane that occupies the two vectors v and b. This force is always perpendicular. The direction is given by the right-hand rule. So for example, one common right-hand rule that we use to determine magnetic force is the right-hand rule, where I have my index finger is the velocity, my three remaining fingers are the magnetic field, and the thumb corresponds to the force. So I have V, B, F. And regardless, some caveats here, as I mentioned, if V and B are parallel, there is no force. But if there's any angle between V and B at all, and that angle could be anywhere from 0 to 180, there's always a force which is perpendicular to the plane, and in this case out. We call that the right-hand rule, gives us the direction. So this is the Lorentz Force law. Sometimes we call it the Lorentz Force. In vector form, if we write this in magnitude, the magnetic force is simply equal to QVB sine theta, where theta is the angle between V and B. Okay, now what happens if that's all and fine if I just have a single charge that's moving, but what happens if instead of one charge, I have a whole bunch of charges that are moving? Then we'd have to calculate the total force. I'd have to add this up a bunch of times, and that's exactly what we do. So I can take the QV and actually replace it with IL. If you think about this, these have exactly the same units. Coulomb meter per second. And here I have Coulomb per second times meter. Whereas this corresponds to point charges, this would be the equivalent for currents. So now I can write my Lorentz Force law for current is IL cross B, where L is the direction that the positive charge is flowing by convention. So F sub I can write as ILB sine of theta in terms of its magnitude. So practically then, what does this look like? Let's just do a quick example here. If I have an external magnetic field pointing to the right, and I have a current I that's moving in the same plane as B, but kind of pointing up and to the right. What direction is the force? Well, to figure out the force, I need to use the right-hand rule. So I would point my fingers in the direction of I, and then I would have to let's see, index finger in the direction of I. My remaining 3 fingers point in the direction of the magnetic field. So my thumb points into the board. I get a magnetic force into the page. So Fi, it would be into the page. And we indicate that oftentimes by a circle with a cross in it would represent a force that is into the page. All right. Finally, in summary here, let's look at one final point, and that is, well, just a note here. The dot corresponds to out of the page. All right. Final point here as we get started would be to take this bar magnet. Imagine what would happen if I bent it into a U shape. Horseshoe magnet. Right, so here's my north pole, here's my south. The reason in practice that you would bend your bar magnet into a horseshoe shape, by putting the 2 poles closer together, you can get a stronger field in the gap, and that field can be more approximately uniform. So I can produce a field that looks something like this. And the idea here is right in between the poles, I get a strong, uniform field. So you will be using this concept of putting a current into a strong, uniform field of a horseshoe magnet to complete the lab for this week. And one thing I should say is we're not going to put a loop of current through here, but we're just going to put a large amount of current through here, and that will allow the force to be somewhat large. If I want a somewhat large force, either I make the field really strong, so we try to make the field as strong as we can, and we try to make the current as strong as we can, and then the force is as large as it can be. You can't make the current too large, otherwise you kind of melt the current. And the angle between L and B is always going to be 90 degrees if we put it right at the center between those 2 poles. Now, what about the Earth? Well, the Earth really just looks like a giant electron in a sense where it is spinning around this axis, but we could ask the question, why is it that there's a magnetic field due to the Earth? And the reason for this is because in the center of the Earth, well, it's rather complicated, but at the most basic level, at the center of the Earth, there is a molten core, which is of iron and other metals which are moving in a very complicated way, but there's a net motion which gives us overall a basically a spinning ball of magnetic dipole moments. Okay, so what does that mean? Well, up here, this corresponds to the geographic North Pole. Here I have the geographic South Pole. Now you might know that the geographic North Pole corresponds to the magnetic South. And the geographic South Pole corresponds to the magnetic North. And the poles the magnetic poles and the geographic poles don't exactly align. In fact, these poles tend to drift a little bit, given by the magnetohydrodynamics governing the core, the molten core of the Earth. And in fact, in the geological past, it appears that the magnetic field has flipped back and forth a few different times. And the period is, well, the period of the flip, from what I understand, does not appear to be anything short. It appears to be, and I'd have to ask my geology colleagues exactly how this works, or if we have a working theory for why this happens, but appears to be on the order of thousands, if not tens of thousands or more years. All right. So this is spinning along, but I don't claim to understand how that flipping process works. But nevertheless, here is the magnetic North Pole. So what we have near the geographic South Pole is we have a bunch of magnetic field lines which are coming out. And those field lines, they wrap around all the way to the top. So that's why if I was somewhere in the northern hemisphere, let's say right here, I would observe a magnetic field that is pointing northward. My compass needle, if I hold the little compass here, the needle would want to line up with the North Pole. And in fact, as long as you're not at the equator, that magnetic field is pointed a little bit down with respect to the horizontal. It's completely vertical when you're at the North Pole. It's completely horizontal when you're at the equator, but there's what's called a dip angle, which can allow you to determine your, roughly can allow you to determine your, well, actually, it's the way it bends here is very nonlinear, but it can give you an indication of whether you're in the North Pole or South Pole, and roughly how north and how far south you are, depending on how much below the horizontal the magnetic field dips. So the Earth's field looks like a giant magnetic dipole. Whereas an electron would be a fundamental magnetic dipole, which has a basic value which, as I mentioned before, can't be any larger or smaller than it is and can only spin in one of two directions. Whereas we could imagine the Earth, corresponding to a bunch of little dipoles, could spin in any direction and spin at any speed. All right, another point, final point here is a Tesla is a really large field. So what we oftentimes do is we define another unit called the Gauss, and 10,000 Gauss we say is equal to 1 Tesla. Now the magnetic field due to the Earth tends to be of the order half a Gauss. Whereas when we're looking at a horseshoe magnet, for example, or some kind of a permanent magnet, we might be able to get magnetic field strength that is, let's say, roughly 1,000 times the Earth's field. That would be a rather strong field. You can get larger than that. If you want to get much larger than that, you have to create an electromagnet, and the strongest types of electromagnets we have would be ones that don't heat up, or what we call superconducting electromagnets, to produce very strong electromagnetic fields. Some of the strongest fields we can produce are on the order of 20 Tesla. This would be superconducting. All right, so that is it for the instruction for magnetic fields. Thank you very much.